Hi, everybody. My name is Max. I'm a security engineer at Figma, and I'm going to present this talk that a colleague of mine, Hongyi Hu, and I put together on navigating the sandbox buffet. This was inspired by the idea that these days there's been a very substantial increase in the number of different sandboxing and isolation technologies that you might be able to use to isolate untrusted software, and that it can be difficult to determine sort of which ones are appropriate to choose to solve a different set of problems. What I hope to achieve with this talk is to convince you that it's useful to isolate untrusted or somewhat dangerous code, and also that the number of these different approaches to doing it don't arise because one is strictly better than the other, but because they actually operate in different places in the trade-off space and let you isolate different kinds of software. I find that the best way to do this is to sort of tell a story of how we might have done this in practice and at scale. So imagine for a minute that we're at a SaaS company in the not so distant past, and someone has written this relatively innocuous looking line of code, which takes an uploaded image from a user, resizes it to a desired size, and stores it back away so that it can then be presumably stored in a database or in a bucket to then be fed back to users. This is the sort of thing that you might reasonably write if you're, say, implementing profile pictures, or you want to thumbnail a file that's been uploaded to you. And this is sort of safe and reasonable to do up until we learn, hey, this is actually calling into this library ImageTragick that has support for 1 million different image protocols, is written in C or C++, and has this series of CVEs in it, one of them relatively famously branded ImageTragick, which allows for sort of arbitrary code execution given a user-crafted image. What we'd like to do, like more abstractly, this is an example of a place where we have the sort of scary code, where scary here means it's processing things that are complicated formats. It's written in an unmanaged language or calling out into sub-processes that have the potential for misuse or for bugs. And we're feeding in sort of arbitrary complicated user input into it. And we'd like to be able to do this safely. We'd like to be able to ensure that the user input that we get, or that we process, doesn't then give that user access to a whole bunch of other data on the system, or to previous users' inputs, or any other things that they aren't supposed to have access to. And we can sort of think about this in practice as you can do this in sort of 2 ways. There's more, I'm sure, but these 2 ways are what we're going to briefly talk about. The first is we can try to harden that scary code. We can restrict which input formats we're willing to accept. Say, with images, we'll only accept JPEGs. We could rewrite libraries like ImageTragick or the Python imaging library in memory-safe languages where certain classes of bugs are harder to do. We can audit them for bugs. We can fuzz them, et cetera. The problem with this approach, which is great, and I think there's a talk about it tomorrow, is that we're presumably a relatively small SaaS company where profile pictures are not our core competency. Resizing images are not our core competency. Or we're doing things like transcoding videos so that we can stream them to your devices, but that's sort of one of many features on our platform. And that's why we've sort of handed it off to a third-party library rather than writing it all from scratch ourselves. So we're not necessarily willing to invest the level of effort that it takes to do that sort of hardening. Instead, what we'd like to do is we'd like to isolate it, which sort of makes us jump back to first principles. Why is it that code execution, or remote code execution, is a problem? On some level, all of us, well, maybe not all, most of us have run arbitrary code from other people on machines that we control. If you visited a website in a web browser that runs JavaScript, you have run those people's code on your machine. Why is RCE bad? The reason we're worried about this is that code that is running sort of on our SaaS services servers has a whole bunch of powers and privileges that sort of attacker-controlled code doesn't necessarily have on their own machines. So for instance, arbitrary code running in our processes can access anything that is in that process's virtual memory. So for instance, Yahoo had a bug a few years back where an uploaded image would give you back, a specially crafted uploaded image would then give you back whatever a recently uploaded image from another user was. You might also have access to local data. So you have secrets presumably stored on your servers, or cached data from previous fetches. Arbitrary code can read that local file system, even though the attacker's controlled code on their laptop can't. If you haven't implemented all the stuff Ian just talked about, you might also be in a privileged network position where you can talk to other services within your production environment and be able to get access to a whole bunch of their sensitive or scary stuff. And what we'd like to do is we'd like to be able to prevent those things. We'd like to get rid of access to local memory, get rid of access to local disk, get rid of access to your privileged network position in a way that gives us high throughput, low latency, and that non-specialist engineers can actually develop in. I say this because often these kinds of processing techniques or processing tools run in places where we're already doing them very close to capacity. For instance, if we're transcoding video, that's a very expensive operation, and we have presumably already paid for roughly the amount of machines that we estimate we need to do the transcoding that we want to do. If we add the security layer that raises the costs of doing so by 5%, by increases the amount of reduces the amount of throughput you need to do by 5%, that's 5% more dollars that we have to spend, and 5% more well, maybe not, 5% more engineering time that you have to spend to make those maintain those machines, keep them up. And also, the engineers that are doing the sort of development inside of these environments that are writing this code may not be experts in how to do this isolation or in how to manage isolated systems. They're experts, presumably, in the thing that you're trying to have them do, rather than in security. So our goal here is going to be, we want to drop those privileges that we described in a way that is fast and a way that is transparent to our end users. And we're going to talk about sort of 3 levels of the security onion here, where we can talk about an option where we isolate the entire operating system, an option where we isolate a group of processes, and an option where we isolate code that is running within one single process. And the first option here we're going to talk about is virtualization, which is the sort of first. We're just taking the operating system. We're going to take a whole machine. Sort of the platonic ideal of isolation is I just buy a new machine for every user request, run the process on that machine, and then throw that machine away. We can't do this with physical machines because it costs a whole lot of money and a whole lot of carbon. And so we'd rather do this with virtualized machines, where I can say, hey, please pretend you're a new computer for me. I have this new user image I want to resize. Give me back the resized image, and then destroy yourself. Or more concretely in code, we initialize a VM, feed it our image, get back our result. Yeah. And this can be great. Your developers, if you're a SaaS product, almost certainly are already familiar with writing code that is meant to run inside of some kind of virtual machine. If you're running in a cloud environment, for instance, all of your machines are most likely virtual machines. And because this is a separate machine, we can control which parts of the host disk and which parts of the host network it actually has access to by configuring our hypervisor or our VM in the appropriate way. Which sounds great. That sort of sounds very, very close to our platonic ideal of buying a new machine and calling it a day. There are a whole lot of downsides here, though. If we think back to sort of what are the things that we wanted to, what are the costs that we wanted to consider, the first one you're talking about is performance. Virtual machines give us this strong isolation because they set up a whole new system every time you want to do some of this processing. And the startup time for one of these virtual machines can be very substantial. This can be measured in seconds or in minutes, depending on the level of complexity that you want to pull in. When you're talking about an operation like resizing an image, transcoding a video, running a computer vision algorithm to do OCR, these are operations that natively happen very, very quickly. Right? Like, it doesn't take very long to take an image in Paint and resize it. That's not an operation that takes very long. So your runtime ends up dominated by startup time if you're starting them up on every request. The developer experience, while great because VMs are highly flexible, has some pretty serious issues. One of which is developers don't write software once, which we'll talk about in just a minute. So how can we sort of fix this? We talked about performance and how we end up with it in the scenario where we're dominated by runtime or by startup performance. We can get away with some sort of fixes here where we can pre-warm our instances. Usually, because we're dominated by startup performance, if we can freeze a virtual machine at the point where it has started but hasn't yet processed a request, and then thaw it and run it that way, we can get much higher throughput, for instance, or much higher latency, but maybe not get throughput because the CPU, we still need to reinitialize a whole new VM every time we get a new image. We could also, instead of kicking off a whole new VM on every user request, we could soften our isolation requirements and say, well, maybe we don't actually need a whole new VM for every image that gets re-uploaded. Maybe we're comfortable with, if it's the same user that's uploading like 12 different images, maybe it's OK that those 12 images are all processed on the same machine. Or they're all in the same organization, depending on your task plan. They can all be processed on the same machine. Or if we're willing to play the probabilistic game, maybe just some number of requests across all of your users. Yes, that still breaks your isolation primitive, where you've traded off some security in exchange for some improved performance. But you no longer have to pay the startup cost for every request, just for 1 out of every 30 requests. And the deeper question is around developer experiences. What do developers actually want? What we learned when we first deployed a virtualization-based system was that it's not that hard to write code that runs in one of these systems the first time. But what developers actually end up wanting is they want to get feedback on whether their system is working well, what the performance characteristics of their systems are. When there's a bug that happens and you get a stack trace back out, they want to be able to attach debuggers and learn things about the currently running state of their programs so that they can fix it. And this is not super well supported if you just build a VM right out of the box. You end up having to do things like punch holes and run additional daemons inside of your virtual machines, or put additional tooling in there that may weaken your security guarantees in ways that you don't necessarily want. So that sort of prompts us to move towards a slightly different world, where maybe we can have better systems in place here if we can at least abstract away the system-level monitoring by saying, well, you don't have to now monitor the status of your VMs and of your hosts. You can now look at the group of processes that you're handling, and that will be your isolation primitive. So you can use all of your standard visibility tooling on the whole system, but you have this sort of security boundary around your process group. In practice, in Linux, this is usually achieved via the use of namespaces. Namespaces are a way of saying, hey, Linux kernel, please, instead of presenting me with the normal file system, present me with this subset, like subdivided view of the file system. Instead of providing me with a view of the whole process tree, give me this subset of the process tree. Instead of providing me with the whole network, give me this part of the network. You might imagine we've rewritten our code here. So instead of calling a resize image function, we instead write some command line like, hey, I'm going to call nsjail, which is a tool by Google that uses namespaces, I think Google, that uses namespaces to do this jailing, with some isolation config, and say, hey, I want to resize this image. Please give me back the output. With namespaces, we get a lot of the isolation primitives that we wanted to get. We're a separate process, because we have run nsjail with /resize image. So we've done a fork and we've done an exec. So memory reuse here is not a problem. We're in a separate mount namespace, which means we get a different subset of the file system. So we don't have access to the whole underlying disk. And we don't have access to the network, because we can restrict which parts of the network you have access to in your network namespace, and which network devices you have access to via your device namespace. This seems strictly better on the surface, right? Like, we have allowed users to get somewhat cheaper, better observability tooling, while still maintaining a lot of the security guarantees. The downside here is we're one level deeper into the security onion. And what this means is that our operating system is shared. And the operating system at issue here, for us at least, was Linux. And Linux has a very, very large attack surface. And it's a very large program that runs in a very concurrent fashion, written in C. It's just very difficult to get this right reliably 100% of the time. There's a lot of attack surface that we have to worry about here. And so there's a lot of escapes of purely namespace-based solutions. One way that we were able to sort of help mitigate that is we can use a system called setcompbpf built into the Linux kernel, which lets us restrict which system calls you're allowed to make. The whole interface you have to the kernel is based around these system calls, these individual essential functions. And we can say, oh, you're only allowed to make this handful of calls. We can restrict arguments to some degree. That gives us some better security guarantees for this system. What overall trade-offs does this make? Well, the good news is our performance here is better too. Instead of our container, or instead of our runtime startup being measured in multiple seconds to minutes, we can be measured here in milliseconds to deciseconds, right? Like a few hundred milliseconds for every startup if you have to spin up a whole new runtime, which is significantly better. We also have some debugging tools that work somewhat better, right? Like you get the same standard system logs as you do if you're not using containers. And if you configure ptrace and friends correctly, you can get them to poke holes through the VMs. But you still will frequently want to do application-specific logs within the system itself. And that poses its own set of hole-punching problems, where you have to open a new file descriptor or pump out logs in your own way. The restrictions we have to do to limit the attack surface also add their own level of complexities. This is one of these things where now the developer experience of your system relies not just on the code itself, but also on the configuration of the underlying host in a way that may not be transparent to developers. So for one concrete instance of this happening, when we deployed a seccomp-based system for the first time, we didn't whitelist the system calls that allow you to get the current time of day because we never saw them called in local development. Unfortunately, the moment we deployed this system to production, we noticed that there were many calls to the system call happening. And this wasn't because the actual code was any different, but because the kernel was configured differently such that it didn't load a special library called the VDSO into our memory space so that we were actually making direct system calls instead of faking them in our own process. These are things that are very difficult for developers to sort of predict, and that you frequently only find out as you're deploying into production. Which brings us to sort of our third approach, which is what if we went all the way deep into the onion? What if we just isolated the individual process? And here we're going to lean on the tool that we use to limit the kernel attack surface in the first place. On a pretty fundamental level, the way that code inside of a process interfaces with the rest of the world and interfaces with these things that are scary is by making system calls. That's what lets them read input, open files, write output, make network calls. And what do we actually need to do if we're doing, say, image resizing? Most of our processing, from the moment we've actually gotten our user input, we might have to allocate some memory. And we probably have to write our output. Maybe we have to read our input if we haven't done that already. What if that's all we did? So we wrote a syscall whitelist that lets you only allocate memory, read from open file descriptors, write to open file descriptors, and then quit. This was actually the idea behind the original version of seccomp called seccomp1 rather than seccomp BPF. The problem with that approach is the original approach does not allow memory allocation, which it turns out you frequently want to do at runtime. Yeah, so this is a system we've deployed now at Figma for our sort of server-side rendering of files. What are the advantages here? Well, for one thing, the performance here is great. All you're doing is you're forking a new process, execing the underlying binary, and then you call seccomp once, and you do your processing, and you're done. Your overhead here is mostly limited to you have to serialize some data back and forth, and there's some limited overhead due to the fork and exec. The downside here is seccomp failures can be very hard to introspect, as we talked about in the sort of previous example, but also not all programs fit cleanly into this box. While programs that are written sort of by your own developers in maybe these unsafe languages can often be rewritten to not require heavy syscall usage deep inside the program, many cannot. So for instance, if you're trying to run a computer vision program, or you're trying to do OCR, or anything that may require, say, the GPU to do its processing, you're almost certainly including a library from a GPU vendor, which may need a whole list of syscalls that you can't get rid of. This limits the utility of this approach in practice, because only a small fraction of your code is likely to be amenable. And then one can sort of think of, well, we talked about this onion. We went through these three sort of examples. Can we go deeper? Is there sort of another level inside of that onion that we could keep going to? And the answer here is probably yes. Ultimately, if you think back to sort of the first example, the very first line of code that we showed, it was making a library call, or making a function call. There's no fundamental reason that a library that is in your shared memory space needs to have access to all of those privileges that the rest of your program has access to. And we might be able to, by recompiling parts of the program, limit the access of these individual functions. This is an active research area. Mozilla has a paper out with UCSD and University of Texas about a system called RLBox that is an example way to do this. We haven't deployed this in production, but we are excited to do so. Yeah. Thank you all.